In this video, I'm going to have a look at the I2C bus and look at how the Atmel implements it. And then we'll do a bunch of software as well. And the final result of this video will be the software to come up with this display here. Now, this breakout board here has three sensors on it: a gyroscope, accelerometer, and a magnetometer. They're all on the I2C bus, and this display is also an I2C display. And they're all being driven by the Atmel on this Arduino board. The advantage of the I2C bus is it only takes two wires, and you can have up to 127, I believe, of different modules on the I2C bus. Now, a couple of years ago I did do a video on the I2C bus, but I felt that I would do another one because it just fits nicely into the Going Beyond Arduino series I've been doing. And if you've already seen that video, then some of this, or quite a bit of this, is going to be a review. But I'm going to go through it anyways. And if you have already seen the other video, just watch this one. You might get some more information out of it. Schematically, this is what the I2C data bus looks like. I'm going to show the microcontroller here, which will be the master. The two lines are S clock or serial clock and SDA or serial data. And all of the devices are hooked up in parallel on the data bus, and so you can have up to 127 different slaves. And then how the slaves are differentiated on the data bus is that each one has a specific 7-bit address, and the master will send out that address, and then the slave that has that address will respond, and all the other slaves will remain silent. And the data bus allows for more than one master, but in this case I'm just going to talk about a single master and a bunch of slaves. Because they're paralleled up, the slaves and the master can only pull the data bus to ground. They can't pull it to 5 volts or whatever VCC happens to be. And so you have these pull-up resistors here from each of the two lines to whatever VCC that you're using. And you got to make sure that the VCC is going to be the same level as the lowest voltage device. And in my case, the display and the sensors are all 3.3 volts devices, and the microcontroller is a 5 volt device. In fact, you may have noticed some extraneous components on the board here. Bring it back in. These parts here, there are two MOSFETs and some resistors, and they're level shifters to shift the voltage from the 3.3 volts up to 5 volts. And I'll include a schematic, and you'll be able to see how I hooked it up. So the data is clocked out at specific speeds. The I2C standard defines these 4 different speeds: 100 kilohertz, 400 kilohertz, a megahertz, and 3.5 megahertz. Most common is 400 kilohertz. I have yet to see any devices that can go this fast. And in this example, we'll be running it at 400 kilohertz. So I've got the clock and the data line here again. And there's a rule that gets broken under 2 conditions. And the rule is that the data must not change when the clock line is high. The data line must be stable, either high or low, when the clock line is high, except for 2 times, and where the rule is broken, and where a start condition is issued. And this is the part of the signaling on the data bus, how the master tells the slaves that something's going to happen. It sends out a start condition. So what it does is it keeps the clock line high and it pulls the data line low. And then it starts clocking out the bits. When it's finished with the data bus, the master will issue a stop condition at the very end, which is just the opposite of this. It holds the data line low and lets the clock line go high, and then it lets the data line go high. So again, the data change while the clock is high, but this is a special condition called a stop. So that's how it signals to the devices on the bus that it's about to start sending data on the data bus. So this is called a start condition, and what follows a start condition is always the same no matter what you're doing on the data bus. It's the same byte that's transmitted. By the way, it's byte-wise transmissions. Everything is done in 8 bits at a time. So the first byte it transmits after a start condition is the slave address of the slave that it wants to talk to. And it's sent out most significant bit first. It's 7 bits, the number that you're given in the data sheet for the peripheral device, or for the slave device, will be left shifted by 1 bit in order to fill in the upper bit here. So this is bit 7 here, and bit 0 is actually here, and it's got a special meaning in the when the slave address is put out. So the slave addresses, the 7 bits of the slave address is clocked out, and then the last bit here is either a 1 or a 0. Yep. Let my charger beep. That's my batteries for my quadcopter, which I'll probably go flying after I do this. And this, either being a 1 or a 0, will signal what the master is going to do. Is it going to read data from a slave, or is it going to write data to a slave? And if it's 0, it's a write. If it's 1, it's a read. And then there's one more clock that comes out, a 9th clock, and that clock is called the acknowledge. And what happens here is that if there is a device on the bus that has this address, it will acknowledge by pulling this line low. And the slave can, or the master can see that, and it can be used for error checking. If there's no device there on the bus that has this address, or no other devices anywhere on the bus, this line will be high, and the master will see that and realize that there's nothing on the bus, or there's no slave with that address, and there's an error, and so you can do something about it. So that is the start condition followed by the slave address. Now, how do you know where you're going to be, what data you're going to be reading out of the slave device? And inside each slave device is an address pointer, and you have to set that to pointing to the address that you're going to start reading from, or the address you're going to start writing to. So generally what happens is you have to set that address, and then the way you do it is, now I've taken away the clock line here. Oops, sorry. I've taken away the clock line in my little drawing here. And so what happens is this sequence of events occurs. Start condition followed by the slave address with the write bit, so it would be low in this bit position here. The slave will respond with acknowledge, everything's happy, the master knows there's somebody out there. And what it does right away after that is it clocks out another byte of data, which is the address that it's going to read from. Now, I should say that the start condition followed by the slave address and the read or write bit is always the same for any slave device. What follows, any data that follows after that, is dependent on the device, and there's no definition in the I2C protocol of what all these bytes mean. You have to look it up specifically for that device that you're using. If this was a really big E² prom, I have some here that have 64 kbytes of data inside them, and so obviously an 8-bit address here isn't going to address all of the data bytes inside the E². And so in the particular EEPROM that I'm using, it's defined that the master has to send out 2 bytes to set the address. In the case of this display, this address is either all zeros or a 1 followed by all zeros, and that determines whether you're writing data, writing commands to the display to get it to do something, or writing data to the display for it to oh, you can't see the display and I'm busy pointing at it here. Put it in here. So what address, so to speak, this address here, what you write to determines whether you're writing command to the display that tells the display to do something, or data, which then gets displayed on the pixels of the display. We'll get into that in more detail later on in the video. So up here I've got a write data, so the master will output the slave address followed by the write bit. The next byte is going to be interpreted as the address by the slave device, and then the slave device is now ready to accept data and starts writing that data to it that it receives, and starting at that address. And the address pointer inside the slave device will increment automatically. And so the master just simply writes out data, byte after byte after byte. And the slave will respond with an acknowledge. It'll pull the line low. And so the master can have a look at that and just decide whether the slave is actually keeping up. And now it'll continue for infinite number of bytes if necessary. but the master is the one that controls it. The slave just has to take whatever the master is sending it. But when the master's decided it sent enough data bytes, it will stop sending the last data byte and then issue the stop condition. Now, to read something out of the slave device, you have to do something a little unusual. Well, some people might consider it unusual. It's going to look the same as when we're writing data, because we have to set that address that we're going to read from. Although, if you, for many devices, if you send out the slave address with the read, and then you just continued reading, the slave device will start outputting data starting at whatever the address pointer inside it was set to the last time. But generally you don't know where that is, so you want to make sure you set it. And so this sequence will do that for you. So you set start condition, slave address with the write, just like up here, and the address you want to read from. Just the same as before. It's identical up to this point. And then what it does, the master does, is it issues another start condition. It's also referred to as a repeated start, followed by the slave address, and this time with the read, and then it just starts continue to clock, clocking the clock line, and the slave will output data to the data bus and it'll get clocked in. And in this case, the master will send out an acknowledge rather than the slave. And at the very end here, when the master has received enough, it will, on the last data byte, it will send out a not acknowledge. That is, it'll let this acknowledge bit go high instead of low, and then it'll issue a stop condition. And what the stop condition does is tells everybody on the data bus that the bus is now free for somebody else to use it if there's multiple masters. So here's the Atmel data sheet. And yes, it's a daunting piece of information, or a daunting document to look through. There's a lot of information in there that, it's a really very, as far as microcontrollers go today, it's a very simple 8-bit microcontroller. There's really not much to it compared to when you look at some other microcontrollers. But nonetheless, this thing's over 400 pages long, so there's a lot of information in here. I'll probably say it more than once through this video, but I encourage you to read this document. Read through it. It's not that hard to do because it's broken up into sections all based on the peripherals. And so what we're looking for the I2C peripheral is actually Atmel's name for it, which is TWI, two-wire interface. So we come down to that. Now, I won't go through any of this because you can read it on your own, but I've already described the general idea. One thing to note is that the 18 mega can only go as high as 400 kilohertz. It can't do the 1 megahertz data rate. But we'll scroll through all of this, and let me see if it's going to be here. I'm looking for a particular thing in the module. Here's a block diagram of it. These are the I/O pins. Oh yeah, this is what I wanted to do. The bit rate generator unit. So it's part of the logic in the 18 mega that generates the clock, and you have to set it up so that it generates the right speed. And the clock is derived from the main CPU clock of the microcontroller. And if you're using an Arduino board, it'll be a 16 megahertz microcontroller. And it takes that 16 megahertz and it divides it down with a prescaler. There's 4 different selections for the prescaler. I'll show you that in a minute. And then it divides it again by the value in something called the TW baud rate register, or bit rate register. And this is the formula that is used to generate the clock frequency that you're interested in. If you rearrange this so that you get TWBR out here, and then everything else is in here, then you can figure out what value you need to put into TWBR based on the frequency that you want to clock the I2C bus at, and also the CPU clock frequency. In my software, I have this little formula written down, so it's obvious what you're doing. Let's go down and have a look at the registers now, because that was one of the registers. So this is the TWBR. That was the register we looked at. It's only 8 bits, but it's used to develop your SCL, or serial clock speed. When you're writing software, the name in the data sheet will be the same name you use in the software. And the compiler knows about these names and does the right thing for you, so you don't even have to think about it. You just, if you want to write to the TWBR, you just say TWBR equals and then the value. So this is one of the registers that you're going to have to work with, but you only have to do it once in your initialization. You don't have to play with it again once you've got your software going. The status register, you'll be using it all the time because this is how you control the I2C peripheral. And, oh sorry, status register, wrong. The status register tells you what the I2C peripheral has just done. And so you will be reading this because you want to know because any errors that occur will come up in the status register here. And so you got to read them looking for errors to make sure nothing went wrong and you can continue on with the next thing. And then here, these two bits in the status register are the prescaler. I talked about the prescaler and how the clock rate was generated. And you have 2 bits, so you have 4 different selections here for the value of the prescaler. So a value of 0, prescaler is 1, which means the 16 megahertz clock is not divided by anything, but it's divided by 1, so it comes out as 16. This is divide by 4, divide by 16, divide by 64. I think in my software I just leave it at 0, which is, I believe, yeah, that's the reset value here. That's what these bits or these numbers here mean, reset value. The next register, you don't have to worry about that one unless you're being a slave, unless you're using the microcontroller as a slave. This is the data register, so data that's to be transmitted gets written to this register, and data that gets read or clocked in from the data bus is read from this register. When the I2C peripheral has done its thing, this register will either be empty if it's transmitted or full of data when it's received. So you'll be reading this one and writing to it quite often as well. And then this is another one, that's the control register. So by setting the various bits in here, you can tell the I2C peripheral what to do. And so there's a feedback here. This bit here is the interrupt. So you can run the peripheral as an interrupt driven as well. We're not doing that here. We're running it in what's called polled, and we're going to be polling this bit because whenever the peripheral is finished doing something you told it to do, it will set this bit. To clear this bit, you simply write 1 to it. It's kind of counterintuitive, but that's the way it works. This bit here is you set it high to enable the acknowledge. If you are receiving bytes, if your microcontroller is receiving bytes from a slave, you need to acknowledge those bytes. So each time you want to read a byte, before you read the byte, you have to set this to high. And then the peripheral will send out an acknowledge, which actually pulls the line low, but you can say this is like enable acknowledge. If you set this bit, the peripheral will attempt to send a start condition on the bus. If you set this bit, the peripheral will attempt to send a stop condition on the bus. WC is an error bit, so if it's set, it means there's been a collision. So the I2C peripheral has tried to do something on the data bus, and it has found out that the data bus didn't respond the way it was expecting. It'll set this bit. And then once you set all these bits, you have to set this bit to tell the peripheral to actually go and do what you want it to do. And then once it's done, when it's done, this will be 0 and the int bit will be 1. Over here is the interrupt enable. So if you're going to use this with an interrupt driven system, you would set this bit and then it enables the interrupts to be used. We're not going to use this bit. And I think that is all of the registers that you have to work with. Yeah, this register we don't have anything to do with that. And then we're done. So there's 3 registers that you have to work with. 2 that you're going to work with a fair bit, and 1 you just set up once. So this is how Atmel has implemented their version of the I2C master and slave. And again, I'm not talking about the slave, so we can ignore all that. And I may do a video on setting up an 80 mega as a slave device. I've done that before. It's a little more complicated, but it's doable. One thing I just thought about here, which I didn't show you. Let's get back to the beginning here. Oh yeah, all the status bits are defined here. Status numbers. Now again, the compiler knows what these numbers are, and there are actual words that you can use to reference the particular type of status. You'll see that in my code. There's something else. Oh, this one I want to show you. So this is how the status works. These values in the ovals are the status. And so when a start condition is issued on the bus, if it was successful, then the status will read, the interrupt flag will be set, and then the status will read this value. You send out the slave address with a write. If the slave acknowledges, you'll get this status. If you don't get an acknowledge, you'll get this status. And if everything's working fine, then you're going to start sending out data. Is that a read? No, it's a write. So we're sending out data. And yes, it's looking for an acknowledge from the slave device. And this is the status you'll get if the acknowledge is there. If there's a not acknowledge, you'll get this value. And anyways, you don't have to worry about these numbers themselves. There's actual names that actually have a meaning to you. So that's what the status looks like. Let's go to Atmel Studio now and have a look at, we'll just look at one software module that I've written, which is the I2C module. And I think after we've looked at this, we'll stop the video, and then on the next video, I'll look at all these other modules. And that, hopefully that'll divide things up into two relatively short videos, less than half an hour each if it works out. So all of this software that I'm going to present to you is mine. I wrote it from scratch. I wrote it by looking through data sheets and studying things and writing stuff and having it crash and fail, and then rewriting it and finally getting it to work properly. It took a while, but I learned a lot. So now if I go to work with some other microcontroller and their I2C peripheral, I can usually get it done really quick because I kind of understand how to do it now, even though their I2C peripherals might be done differently than the way Atmel's done it here. So let's have a quick look here. So there's an initialization routine here, and it takes a value called I2C speed, which is the clock speed that you want to use, and you write it out completely, all like 400 kilohertz. So it's 4000000. Is that right? Anyways, 4 followed by 5 zeros. And then it reads that and it uses it in this formula. So this is the rearranged formula that I showed you from the data sheet. And the compiler will look at FCPU, which is defined, and I'll show you about defining it again. How to define it. You notice you didn't see it up here at the beginning of my code. Anyways, the compiler will see this and it'll do the calculation, and it does not create code to do this calculation. The compiler does this calculation and just comes up with a number, which then gets written to the baud rate register. I keep calling it a baud rate, it's not correct, it's bit rate register. FCPU, I've talked about this in other videos, but I'll review it again here. FCPU is a defined value that the compiler uses in many different software modules. And rather than having to define them in every software module, and then suddenly you want to use a different clock speed because you've got a different kind of microcontroller set up, then you'd have to go into all those modules and edit each one of the define FCPU whatever value. And so what you do is you go into the project and the sensor's property, the project properties. It brings up this tab. Click on toolchain, and you go down into the C compiler section and you look for symbols. Click on that and you'll see FCPU is defined here. Well, I wrote that. I put that in there. So the way you do that is you click on add item, you type in what you want to add, and it has to look like this. Something equals a number or something else. It could be anything you want. And there could be many of them here. This one, I just put in one. And then when you click OK, it'll put it in here. If there's a mistake, you can edit it with this little pencil item here. And then I can edit this and change it if necessary. One more thing that might be useful for you to define. Now the way I arrange my software, my source code, I have a directory called AVR code /avr, and then slash, and there's a whole bunch of subdirectories in there, and each subdirectory is for for each different software module that I'm using. So for example, the I2C module is in its own directory where you'll find I2C.c and I2C.h. And so I keep all of my software drivers in one area of my computer, and instead of having to type in the whole path name at the beginning here, for example, like that, I would have to type in C:/ blah 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 blah. I don't want to do that every single time, so what I do is I go into this tab under directories, again under the compiler, and I put in the root directory for all of my software libraries. And again, it's done the same way. A plus adds the item. If you want to delete it, that's how you do it. If you need to edit, you click on this tab. So all I have to do when I include it, say let's look at the main source here, I simply have to write in the subdirectory followed by the file that I want to include. And I don't have to type in the whole C:/ yada yada yada. And if I happen to move those for some reason, I don't have to go around and change all of my source code, which could be, as you can see here, there is quite a number of files that are associated with this one project. So imagine the chore I'd have to go through and change all of these addresses. So you do that in the project here. A couple of shortcuts. Once you understand how you're doing this, it makes your coding a lot easier to work with. You have to save it. If you make changes here, you have to save it. So let's look at I2C, and we'll end the video after we've looked at this. So initializing is done here. You got to set the I/O pins as inputs and disable the pull-ups. The microcontroller has internal pull-up resistors, and it pulls it up to whatever the VCC of the microcontroller is at. In that little setup I showed you at the beginning of the video, microcontroller is at 5 volts. All the other devices are at 3.3 volts. Not a good idea to be pulling them up to 5 volts. Not every 3.3 volt device has 5 volt tolerant inputs, and so don't assume that. So anyways, I disable those. That's the initialize. You got to call this before you do anything with the I2C bus. Now the next function here is called I2C Start, and it simply tells the peripheral to put a start condition on the bus. And so I explained how you set those bits. TWINT, you have to clear it. TWSTA is the start, enable the start bit, and then enable the or basically tell the peripheral to do its job. Now it takes a bit of time for that start condition to be issued onto the data bus, and the microcontroller can operate way faster than that. And so you have to stop and wait for a while here until the TWINT flag is set. So that's what this line here is for. You'll notice my coding style. I put the curly brackets in here. You'll probably see tons of code online where they put a semicolon here. That's great. That's a nice shortcut, but you got to know what you're doing, because if you forget that semicolon, what happens then is the next statement in line, and in this case it's the switch statement, is going to get executed every time through this loop. You may not want that to happen. So what I do is I put in the curly brackets to tell me and anybody else that reads this code that the while loop is doing nothing, because there's no statements in here. Recommended practice. In fact, when I'm working professionally and I have to write software, I have to write to certain coding standards. It depends on the company I'm working for, and most companies want me to do it this way. Just reduces the number of mistakes. So we're sitting here wasting time, basically. The microcontroller is not doing anything else unless you've got interrupts running, and then you could do interrupts in this time here, but it's blocked here. The microcontroller can't do anything else. Once the TWINT bit is high, then you can check the status and see what happens. So these two here are good things. The start or the repeated start condition occurred, and therefore I return 0. So you may have noticed I've made this function here return a value. it returns an error code. So a 0 means there was no error, and a non-zero number means an error. And I've written a number of my functions that do that for you. It's just a good way to write your code so that you don't just go flying through the code not realizing that something went wrong and still try to write data out to the data bus and get weird results. So I have a way, now I've given a way that the main code can check all this and do something if something went wrong here. So if any other status occurred, which shouldn't occur if the start condition was successfully put on the data bus, then you shouldn't get to anything else. The stop condition is very similar, except you use the STO here. There's no status returned, so I don't bother checking for it, and I don't return any error condition. And the next one is put car, and it just means put one byte out onto the data bus. And that byte could be the slave address plus the read-write bit, or it could be data, or it could be whatever. But this is writing to the data register, so the character C is brought in, and it gets put immediately into the data register. And then I clear the interrupt flag as before, and then I set the enable again as before. And also in this case I return an error code. Again, like before, I sit here waiting for the peripheral to do its thing, and clocking out 8 bits of data at 400 kilohertz is pretty slow compared to what the microcontroller can do at 16 megahertz. So the microcontroller is going to sit here twiddling its thumbs for quite a while, at least in microcontroller terms, before the interrupt flag gets set, and then it falls through and it checks the status. And so if any of these statuses come through, then it was successful. It wrote the byte successfully. If anything else, it returns an error code. I should clarify what this _BV, again, it's another thing that comes with the compiler. It's already defined, but what it means is a 1 left shifted by the number of positions that's in this value here. So it would look like this. So I could say 1 left shifted TWINT, and that's a valid statement. Well, it'd have to be equal to something, so I could, let's do this, TWCR equals that. So this is the same as that. That's all this BV means. I think it stands for bit value, but it's a nice little shorthand way of doing something like this instead of typing all of this. The OR symbol here, this is the vertical line is an OR, so it means this, 1 left shifted by TWEN. Oops, forgot something here. Gotta put the OR symbol in. So what it means is, what you're going to get when you do this is you're going to have all zeros, a byte that has all zeros, except for the 7th bit will be set. And in this one, all zeros except for the 2nd bit. And then when you OR them together, you'll get a byte with both those bits set. So that's all that this statement does. Put car. Get car is just the opposite, reading a character from the data bus. In this case, I call it get car ACK. It also returns an error code. And what get car ACK does is it puts out an acknowledge on the acknowledge clock time, the 9th clock. Basically, the control register is given this this information. Again, you clear the interrupt flag. This time we're going to enable the acknowledge and then return the turn the peripheral on, get it to do its thing. With it'll clock out the clocks, and then the slave will write data to it, and it'll clock in the data. Again, it has to wait for all this to occur, and then finally it just reads whatever's in the data register. So you notice the data register is read here and written to here. Actually, I was wrong. This is not an error code here in this case. This is the value that you get from the data bus. So I don't do any error checking here. I could, and I'd have to put that into a global or a local variable in this module, and then you'd have to read it some other time. Probably an extension I could do to this code to make it more functional. But for now, this seemed to work. I've been using this code for quite a while, and this seems to work. This stuff will be on my GitHub site. You guys can copy it and do whatever you want with it. Play with it, improve it. Don't sell it though. It's free, so don't try to make any money off of it. Getcar knack is just the same as getcar ack. In this case I said a knack instead of an ack. Does the same thing. Now, to do what I showed you in those little timing diagrams, the earlier part of this video, I can put it all together. So this is I2C write. So this means write a bunch of bytes to a particular address in the slave device. And so it's a function that's called with 4 parameters. The first one is a slave address, the 7-bit slave address. The second one is the number of bytes that you're going to write. I should probably correct that. As you can see, if you notice the date in this thing, it was 7 years ago or 6 years ago that I was working on this. I made a few mistakes and haven't corrected them. Not a big deal. Anyways, length is the number of bytes that you're going to be writing. The address is inside the address inside the slave that you're going to write to, and then the buff is a pointer to a buffer that contains the bytes you're going to write. Now, I do quite a bit of error checking here because I want to make sure this works. First thing I do is if length is 0, I return 0. I don't do anything. There's no bytes to write. Although one thing about this, I could rewrite this and have this check later on. I have no way of just setting the address inside the slave device and then doing nothing if I want to use it later on. But it doesn't really matter. Thinking out loud here, don't worry about it. Ignore me. So here's the steps that it follows. Applies a start condition, puts a slave address with the write bit set, so write is 0. And then it puts the byte address or the address inside the slave device onto the bus, and then it puts a number of data bytes on the bus. And when it's finished putting that number of data bytes on the bus, it applies a stop condition. And so you can see how it's done in the code here. Here's the start condition. So this weird stuff here with this label write restart. There's a goto here. Now gotos are not they're implemented in C, but they're not the best way to do things. But I couldn't figure out a better way to do this. But what I do here is if the I2C Start issues an error, I check that error and then I decrement it. So if there's an error, it'll go into this if statement in here and it'll decrement restarts. And then and I got a certain number of restarts here, which already defined here. Max restarts, I think it's 20. I do this because you could have this repeatedly sitting in here doing nothing, or running through this loop over and over again and blocking the microcontroller. And so I had a way to get out of here so this doesn't hang forever. So what happens is it goes through this loop. If there's an error in the start condition, it keeps trying. It'll try 20 times, and then finally, if it doesn't make it after 20 tries, issues a stop condition and returns an error code. That's all it does here. Here we're going to put the slave address left shifted by 1 bit and ORed with the TW right. So there's a 0 there. It's just going to put a 0 in the right hand bit, the lowest order bit. And again, I do a similar kind of loopy thing here. If it doesn't put this on the bus correctly, if there's an error, put car returns an error, it's going to decrement restarts, and then eventually if it fails too many times, it'll hit stop and then it'll return an error code. If it's successful, it goes on. And now it puts out the address that you're going to write to. I don't bother to do any more error checking after this point. It's getting complicated. Actually, what happens here is if there is an error, it goes right back to up here, right restart. It reissues the start condition and then the put car again. Again, like I said, this is the best way I could come up with how to write this effectively. Maybe there's a better way to do it, but if you find something, let me know. If you find a better way of doing this. So it writes the address to the bus that you're going to write to inside the device, and then here in this loop, for a length number of times, it just outputs the data to the bus. And again, if there's an error, and any time that this error is out for some reason, it returns immediately with an error code. I should probably put a stop in here as well, which I haven't done. But anyways, not a problem. I'm assuming it's successful. It loops through here for each of the data bytes it's writing out to the device, and then it finishes and it issues a stop condition and returns with no error code. So that's how I2C write works. I2C read is very similar, except it has one extra step. So again, we apply a start condition, then the slave address with the write bit, followed by the address that you want to read from. And then you apply another start condition, which is also referred to as a repeated start. The slave address again, this time with bit 0 equal to 1, which means we're going to read. And then receives a number of data bytes except for the last one that it wants to read, and it acknowledges it. And then it reads the last one it wants to read with a not acknowledge, and then finally puts a stop condition on the bus. The parameters are the same as the previous one: slave address, the number of bytes it wants to read, the address it wants to read from, and a buffer to store them. Some words of caution here: make sure that buff is big enough to hold the number of bytes that you want to read. C compiler does not check for that and won't tell you that you've goofed up. If you have a buffer that's too small and you overwrite it past the end of it, you could write variables that are used by something else in the program, and you could cause some crazy results or your program to crash. So make sure buff is big enough. And when I'm beginning this code, I'll actually make buffer quite a bit bigger, just to make sure that there's no problem. And as I get things working, I'll shrink the size of it down to the right size. Again, the same kind of error checking here. Start condition, if there's an error, tries a bunch of times. Slave address with the write, tries a bunch of times here. Again, returns error codes if there's an error. Finally gets through all that, puts out the address onto the bus, and then it issues another start condition and another slave address, this time with the read bit set. Again, if there's any errors, it doesn't even retry. It just done, error, return with an error code. Get out of here, let's deal with it. And then it outputs all the bytes but one with an ACK, and then the last one with a NACK, a not acknowledge, finally the stop condition, and then return 0, no error. So that's how my I2C software works. Again, it's my code. I wrote myself. If there's a better way of doing it, by all means do it. If you do find a better way, you've got some better ideas, let me know. I'd like to hear from you. So I'm going to stop the video here, and there's a lot of information for you to absorb, so I encourage you to look at the links down below, look at the datasheet, and look at the Wikipedia page on the I2C bus. Thanks for watching. Stay tuned for the next one. Part 2 coming up.